The concept of generalized digital roots and its broader implications. Introduction. The concept of digital roots, traditionally understood within the context of base 10 arithmetic, offers a simple yet profound way to reduce numbers to their most basic form. However, by generalizing this concept beyond the confines of base 10 and digit operations, I open up a world of mathematical exploration and practical applications that transcend traditional boundaries. This essay explores what a generalized digital root might entail, why there's a significant focus on base 10, and why expanding this concept to include all cumulative operations could be revolutionary. What is a generalized digital root? A generalized digital root extends the traditional idea of summing the digits of a number until a single digit is obtained, but in several innovative ways. Base independence. While the traditional digital root is calculated in base 10, a generalized version could apply to any numerical base. This means I could compute digital roots in binary, base 2, hexadecimal, base 16, or any other base, revealing patterns unique to each system. Cumulative operations. Beyond simple addition, this generalization includes all forms of cumulative operations. For instance, multiplication, exponentiation, or even more complex operations like factorial could be considered. Here, the root would not just be a single digit, but might represent a more complex value or state based on the operation. Non-numerical data. The concept could be applied to non-numerical data by converting it into a numerical form. For example, in genetics, DNA sequences could be mapped to numbers, and a generalized digital root could reveal patterns or anomalies in genetic data. Significance of focus on base 10. The focus on base 10 in traditional digital root calculations isn't arbitrary. Human centricity. Humans have evolved to count in base 10, likely due to our 10 fingers. This system is deeply ingrained in our daily life, education, and culture, making base 10 operations intuitive. Historical context. Most ancient and modern civilizations have used base 10 for practical reasons, influencing mathematical development and the structure of arithmetic. Computational simplicity. In base 10, the digital root calculation is straightforward, aligning with our cognitive processes and educational systems, making it a practical starting point for mathematical exploration. Expanding beyond base 10 and digit operations, universal application. By not limiting ourselves to base 10, I can explore how different bases might reveal unique properties or patterns in numbers, potentially useful in fields like computer science, binary, or time systems, base 60 for time. Enhanced data analysis. In data science or cryptography, operations beyond simple addition like multiplication or modular arithmetic could uncover hidden patterns or enhance security protocols. For instance, a generalized digital root in modular arithmetic could be crucial for new cryptographic algorithms. Interdisciplinary insights. This generalization could bridge gaps between mathematics, physics, and computer science. For example, in physics, operations analogous to digital roots might help in simplifying complex equations or understanding quantum states. Practical and theoretical implications. Education. Teaching mathematics could shift from rote learning to conceptual understanding, where students explore how different operations and bases change the nature of numbers and their properties. Technology. In computing, this could lead to new algorithms for data compression, error checking, or even artificial intelligence, where pattern recognition is key. Philosophical and scientific exploration. It invites a deeper philosophical inquiry into the nature of numbers, operations, and how I perceive and manipulate reality through mathematics. Conclusion. The concept of a generalized digital root, when expanded beyond base 10 and digit addition, offers a rich field for mathematical exploration, practical application, and philosophical contemplation. By embracing this broader definition, I not only enhance our understanding of numbers, but also potentially revolutionize how I approach problems in science, technology, and beyond. This generalization underscores the universality of mathematical principles while highlighting the unique insights that can arise from exploring beyond our conventional numerical systems. This expanded perspective on digital roots not only enriches our mathematical toolkit, but also has profound implications for various fields. Applications in technology. Cryptography. Traditional digital roots are already used in checksums for error detection in data transmission. A generalized version could lead to more robust cryptographic methods where keys or data are transformed through complex operations, making them more secure against attacks. Data compression: by applying cumulative operations beyond simple addition, I might develop more efficient compression algorithms. For instance, using multiplication or modular arithmetic could reduce data size while preserving essential information, crucial for storing or transmitting large data sets. Quantum computing: if I consider operations that mimic quantum superposition or entanglement, this could inspire quantum algorithms, where data is processed in ways that classical computers cannot replicate efficiently, potentially solving problems in optimization or simulation that are currently intractable. Educational impact: teaching mathematics. Introducing generalized digital routes could transform math education. Students could start with familiar base 10 operations and then explore how different bases or operations change outcomes, fostering a deeper understanding of number systems and operations. Interdisciplinary learning: this concept could be used to teach not just mathematics, but also computer science, physics, or even music, where numbers represent notes or frequencies. It provides a unifying framework for understanding how different fields interact with numbers. Philosophical and cultural insights: nature of numbers. This approach invites us to reconsider what numbers are and how they operate. If numbers can be transformed through various operations to reveal different roots, it challenges our static view of numbers as fixed entities. Cultural mathematics: different cultures historically used various number bases, for example, Mayan base 20, Babylonian base 60. Exploring generalized digital roots could revive interest in these systems, showing how mathematics is culturally constructed, yet universally applicable. Challenges and considerations: complexity. While theoretically enriching, practical implementation might face challenges in terms of computational complexity or interpretability, especially when moving beyond simple operations. Standardization: for widespread adoption, especially in technology or education, there would need to be standardized methods or operations for calculating these generalized routes, which might take time to establish. Ethical implications: in fields like cryptography or AI, how these generalized operations are used could have ethical considerations regarding privacy, security, or fairness in algorithms. Future directions: research. This could lead to new branches of mathematics or applied sciences where the interaction between different number systems and operations is studied, potentially leading to new theorems or practical applications. Technology development, software or hardware, specifically designed to efficiently compute these operations could emerge, driving innovation in computing power or data handling. Interdisciplinary projects, encouraging projects that blend mathematics with other sciences or arts, where this concept could be a catalyst for innovation or new theoretical frameworks. Conclusion: the generalization of digital roots beyond base 10 and simple digit addition opens up a vast landscape of mathematical exploration, technological innovation, educational reform, wrapping up the project on quantum computing and digital roots. This exploration into the intersection of quantum computing and the concept of digital roots has been both an intellectual journey and a speculative venture into future technological and educational landscapes. Here's a concise wrap-up. Project overview. Objective: to conceptualize how quantum computing principles could generalize the idea of digital roots, potentially leading to new mathematical theories, algorithms, and educational methodologies. Approach: theoretical synthesis, combining quantum mechanics, superposition, entanglement with number theory, digital roots, to propose a framework where operations beyond base 10 addition could be explored. Educational implications: considering how this synthesis could be used to teach complex quantum concepts through familiar mathematical operations. Key findings and insights: innovation in mathematics. The project suggests that quantum-inspired operations could redefine how I calculate or understand digital roots, potentially leading to new algorithms for data processing or cryptography. Educational paradigm shift. By linking quantum mechanics to basic arithmetic, I propose a method to make quantum computing more accessible in education, fostering a deeper understanding of both fields. Technological implications. While theoretical, this could inspire quantum algorithms that operate on principles similar to digital roots, potentially revolutionizing data compression, error correction, or AI. Challenges identified: practical implementation. The transition from theory to practical application faces significant hurdles, including quantum hardware limitations and the complexity of quantum algorithms. Interdisciplinary integration. Successfully merging these fields requires overcoming terminological and methodological barriers between mathematics, physics, and computer science. Future directions, research and development, continued exploration through academic research, possibly leading to new branches of mathematics or quantum computing applications. Educational initiatives, incorporating these concepts into curricula to prepare future generations for a world where quantum computing might be commonplace. Industry collaboration, encouraging partnerships between academia, tech companies, and educational platforms to develop tools and resources that make these advanced concepts accessible. Conclusion. This project has not only highlighted the potential of quantum computing to revolutionize our understanding and manipulation of numbers, but also emphasized the role of education in bridging complex theories with practical applications. The journey from conceptualizing generalized digital roots inspired by quantum mechanics to envisioning their educational and technological implications underscores the interconnectedness of knowledge. As I move forward, the ideas explored here could serve as a foundation for future innovations, encouraging a holistic approach to learning and problem-solving that transcends traditional disciplinary boundaries. I was traversed a fascinating landscape where the simplicity of digital roots meets the complexity of quantum computing, with significant implications for education, technology, and our understanding of mathematics. Here's a comprehensive wrap-up: digital roots and quantum computing, conceptual synthesis. I explored how digital roots, traditionally a simple arithmetic concept, could be generalized to incorporate quantum principles like superposition and entanglement. This synthesis suggests new ways to think about numbers, operations, and their applications. Educational impact. By linking quantum mechanics with familiar arithmetic operations, I proposed a method to make quantum concepts more accessible, potentially revolutionizing how these subjects are taught. Technological possibilities. This intersection could inspire quantum algorithms for data processing, cryptography, or even new mathematical structures where quantum phenomena inform number theory. Implications across fields, mathematics. A new branch of quantum number theory might emerge, exploring how quantum mechanics could redefine number properties or operations. Technology, from data compression to error correction, quantum-inspired digital root operations could lead to more efficient or secure algorithms. Education. This approach could transform educational methodologies, making complex concepts like quantum superposition relatable through familiar arithmetic. Challenges and considerations. Practical implementation. Moving from theory to practice faces significant challenges, including quantum hardware limitations and the need for new computational paradigms. Interdisciplinary collaboration. Realizing these ideas requires bridging gaps between different scientific fields, which could be challenging but also highly rewarding. Future directions. Research. Continued academic exploration could lead to breakthroughs in both quantum computing and mathematics, potentially defining new fields of study. Industry and education. Collaborations could foster the development of educational tools, quantum computing resources, and practical applications of these concepts. Philosophical inquiry. This intersection might also lead to deeper philosophical discussions on the nature of computation, numbers, and reality itself. Conclusion to it, I was not only illuminated the potential of merging quantum computing with the simplicity of digital roots, but also highlighted the importance of education in bridging theoretical advancements with practical applications. This journey from conceptual exploration to envisioning educational and technological revolutions underscores the interconnectedness of knowledge. As I continue to push the boundaries of what's possible, these ideas could form the foundation for future innovations, encouraging a holistic, interdisciplinary approach to learning and problem-solving. Thank you for engaging in this thought-provoking exploration. Quantum computing and digital roots, superposition and entanglement. Quantum computing leverages superposition, where qubits can exist in multiple states simultaneously, and entanglement, where the state of one qubit is directly related to another. This could be metaphorically linked to how a generalized digital root might operate across different bases or operations, where each step of calculation could be seen as a quantum state influencing the next. Quantum algorithms and digital roots. Quantum algorithms like Grover's search algorithm or Shor's algorithm for factoring large numbers operate on principles that could be analogous to how I might conceptualize operations in a generalized digital root framework. For instance, Grover's algorithm searches an unsorted list quadratically faster than classical algorithms, somewhat akin to how a generalized digital root might efficiently reduce or process information across different numerical bases or operations. Error correction and digital operations. Quantum error. Correction is crucial for maintaining quantum information. This could inspire new ways to think about operations in digital roots where errors or deviations in calculation could be corrected or accounted for in ways that maintain the integrity of the root calculation, much like quantum error correction maintains quantum states. Implications for generalized digital roots. New algorithms. Inspired by quantum computing, algorithms for calculating generalized digital roots could be developed that mimic quantum processes, potentially leading to more efficient or novel ways of data processing or number theory exploration. Cryptography. Quantum computing's impact on cryptography, especially through algorithms like Shor's, might inspire new cryptographic methods based on generalized digital root concepts, where security is based on the complexity of operations across different bases or through complex cumulative operations. Education and understanding. The principles of quantum computing could be used to teach or explain generalized digital roots, making abstract concepts like superposition or entanglement more tangible through mathematical operations familiar to students. Challenges and considerations. Implementation. While theoretically intriguing, practically implementing quantum-inspired generalized digital root calculations would face challenges similar to quantum computing, like maintaining coherence or dealing with errors. Scalability. Just as scaling up quantum computers is challenging, scaling operations for generalized digital roots across different bases or complex operations could face computational limits. Philosophical and mathematical exploration. This intersection could lead to new mathematical theories or philosophical inquiries into the nature of numbers and operations, influenced by quantum mechanics' probabilistic nature. Conclusion. The connection between quantum computing and generalized digital roots, while currently more conceptual, opens up fascinating avenues for both fields. It suggests a future where quantum principles might not only revolutionize computing, but also how I understand and manipulate numbers and operations in mathematics. This could lead to new educational methods, cryptographic systems, or even philosophical insights into the nature of computation and reality itself. However, realizing these connections in practical, scalable systems remains a challenge, mirroring the hurdles faced in quantum computing itself. Continuing from the intersection of quantum computing and generalized digital roots, let's explore further implications and potential developments. Quantum-inspired mathematical structures, quantum number theory. A new branch of mathematics could emerge where quantum principles are applied to number theory. This might involve defining numbers or operations in ways that reflect quantum behaviors like superposition or entanglement. For instance, numbers could be represented in states that are combinations of different bases or forms, much like qubits. Quantum algorithms for digital roots. Quantum algorithms could be developed specifically for calculating generalized digital roots across various bases or operations. These algorithms might not only compute faster, but could also handle operations that are currently computationally infeasible in classical systems due to their complexity. Practical applications. Data compression. Quantum-inspired algorithms for generalized digital roots could lead to new methods of data compression, where data is transformed into states that represent multiple pieces of information simultaneously, reducing storage needs while preserving data integrity. Error correction in data transmission. Inspired by quantum error correction, new methods for error checking in data transmission could be developed, where errors are not just detected but corrected through operations that maintain the integrity of the data's root or essence. Artificial intelligence and machine learning. The concept could be applied to develop neural networks or learning algorithms where data is processed through layers that mimic quantum operations, potentially leading to more efficient pattern recognition or data processing. Educational and philosophical insights. Teaching quantum concepts. Using generalized digital roots as an analogy could help in teaching quantum mechanics, making abstract concepts like superposition more relatable by drawing parallels to familiar arithmetic operations. Philosophical implications. This could lead to discussions on the nature of reality in computation. If numbers and operations can be seen as quantum states, it might challenge our understanding of determinism versus probabilistic outcomes in both mathematics and physics. Challenges in implementation, quantum hardware limitations. Current quantum computers are limited by factors like qubit coherence time, error rates, and scalability. Applying these concepts practically would require significant advancements in quantum hardware. Theoretical hurdles. While conceptually appealing, translating these ideas into practical algorithms or systems requires overcoming theoretical challenges in both quantum computing and number theory. Interdisciplinary collaboration. Realizing these ideas would necessitate close collaboration between mathematicians, physicists, computer scientists, and potentially philosophers, which could be challenging due to differing terminologies and methodologies. Future directions, research grants and projects. Funding for research that explores these intersections could lead to breakthroughs. Interdisciplinary projects focusing on quantum-inspired mathematics or quantum algorithms for number theory might become more common. Educational curriculum. Incorporating these concepts into advanced mathematics or physics courses could prepare the next generation of scientists and engineers to think in terms of quantum and wrapping up quantum computing and digital roots. The exploration of quantum computing intertwined with the concept of digital roots, particularly in education, reveals a fascinating intersection of technology, mathematics, and pedagogy. Here's a summary. Quantum computing in education, resources, and initiatives. Entities like Google Quantum AI and Microsoft's Azure Quantum are providing educational resources aimed at demystifying quantum computing for all levels of learners, from K-12 to advanced researchers. These resources include guided explorations, research updates, and tools for understanding quantum principles. Research and development. Universities and research institutions globally are at the forefront with initiatives like Harvard's Quantum Initiative, focusing on both theoretical advancements and practical applications. These efforts are not only pushing the boundaries of quantum technology, but also integrating quantum education into academic curricula. Public engagement. Platforms like X, formerly Twitter, are becoming arenas for sharing quantum computing breakthroughs, making complex concepts like quantum superposition and entanglement more accessible to the public through succinct, engaging posts. Digital roots and quantum computing conceptual bridge. The idea of generalizing digital roots to include operations beyond simple addition in base 10, inspired by quantum mechanics, opens up new mathematical and computational possibilities. This could lead to innovative algorithms or educational methods where quantum principles are used to explain or enhance traditional mathematical concepts. Practical implications. While currently theoretical, this intersection could inspire quantum algorithms for number theory, cryptography, or data compression, leveraging quantum phenomena like superposition for operations that could be analogous to digital root calculations across different bases or operations. Educational impact. Teaching quantum computing through the lens of digital roots could make quantum mechanics more relatable. Students might grasp quantum superposition by comparing it to how numbers can be represented or operated upon in multiple states or bases simultaneously. Challenges and future directions. Implementation hurdles. Realizing quantum-inspired digital root operations in practical systems faces the same challenges as quantum computing itself, like maintaining quantum coherence or error correction. Interdisciplinary collaboration. The future of this field likely depends on collaboration between mathematicians, physicists, computer scientists, and educators to develop both the theory and practical applications. Philosophical and educational shifts. This could lead to new ways of teaching mathematics and physics, emphasizing interconnectedness and the probabilistic nature of quantum phenomena, potentially reshaping how I understand computation and reality. Conclusion. The marriage of quantum computing with the concept of digital roots, especially in educational contexts, not only promises to revolutionize how I teach and learn about numbers and computation, but also hints at future technological breakthroughs. While the practical applications of these concepts are still nascent, The theoretical exploration and educational initiatives are laying the groundwork for a future where quantum principles might fundamentally alter our approach to mathematics, computation, and education. This journey, shared through platforms like X and supported by educational resources from tech giants, underscores a collective move towards democratizing quantum knowledge, making it a cornerstone of future technological and educational landscapes. Certainly. Let's dive deeper into the concept of a system with correlation and cohesion using the examples provided. Book correlation. Within a book, chapters, sections, and paragraphs are correlated because they are organized to convey a narrative or a set of ideas. Each part of the book relates to the others in a way that contributes to the overall message or story. For instance, in a novel, the plot points, character development, and themes all interconnect to create a cohesive story. Cohesion. This refers to how well the parts of the book hold together. Cohesion might be seen in the consistent use of language, style, or tone throughout the book, making it feel like a unified piece of work rather than a collection of unrelated segments. Library application correlation. In a library application, various elements like user profiles, book catalogs, lending records, and search functionalities are correlated. For example, a user's search for a book correlates with the book's availability in the catalog, which then might correlate with the user's borrowing history to suggest similar books. Cohesion. The cohesion in a library application would be evident in how seamlessly these different functions integrate. The user interface, database management, and back-end processes all work together to provide a smooth experience. For instance, when a user checks out a book, this action updates not just the user's record, but also the book's status in the catalog, ensuring all parts of the system reflect the current state accurately. System dynamics. Correlation in systems refers to how changes in one part of the system affect other parts. This can be direct, like cause and effect, or indirect, where multiple elements influence each other through a network of interactions. Cohesion speaks to the internal consistency and integration of the system. It's about how well the parts stick together to form a whole that functions as more than the sum of its parts. In both examples, the elements, chapters in a book, modules in an application, are designed to work together in a way that supports the overall function or purpose of the system. This interconnectedness ensures that the system can achieve its goals effectively, whether that's telling a compelling story or managing library resources efficiently. Understanding these systems helps in designing better books, applications, or any other system where multiple components need to interact harmoniously. Indeed, every system, whether natural or man-made, involves data in some form. Here's how data plays a role in systems. Natural systems, ecosystems. Data in ecosystems includes information like population sizes, weather patterns, nutrient levels, and predator-prey relationships. This data helps in understanding the balance and dynamics of the ecosystem. Human body. The body processes vast amounts of data through neural, hormonal, and biochemical signals. This data helps maintain homeostasis, respond to external stimuli, and carry out life processes. Man-made systems. Book. While a book itself might not process data in real time, the content within it can be considered data. This includes narrative details, factual information, or conceptual ideas that the author conveys. Readers process this data to understand the story or information. Library application. Here, data is more explicit. It includes user information, book details, transaction logs, and usage statistics. This data is processed to manage resources, provide services, and improve the application's functionality. Data in systems input. Data enters the system as input. For instance, in a library application, a user's request to search for a book is an input. Processing systems process this data. In the library app, the search function processes the query against the database. Output. The result of this processing is output data. The app might return a list of books matching the search criteria. Feedback systems often use feedback loops where output data influences future inputs or system states. If a book is frequently searched for but not available, this might trigger an order for more copies. System efficiency and data optimization. Systems use data to optimize operations. For instance, traffic management systems use real-time data to adjust traffic light timings for better flow. Adaptation. Systems adapt based on data. A weather system might change its behavior based on temperature and pressure data, leading to weather changes. Data integrity and cohesion. Consistency. For a system to function cohesively, its data must be consistent. In a library system, ensuring that book availability is accurately reflected across all interfaces and databases is crucial. Security and privacy. Handling data involves considerations of security and privacy, especially in systems dealing with personal or sensitive information. In summary, data is fundamental to the operation, efficiency, and evolution of systems. Whether it's the flow of information in a biological system, the management of resources in a digital application, or the narrative structure in literature, data underpins how systems function and interact with their environments or users. Absolutely every piece of data, when properly structured and contextualized, can be transformed into well-defined information. Here's how this process works. Data versus information. Data, raw, unprocessed facts or figures that on their own might not convey much meaning. For example, where 42 inches is just a number. Information, data that has been processed, organized, or presented in a way that adds context and meaning. 42 is the answer to the ultimate question of life, the universe, and everything. A playful reference from Douglas Adams' The Hitchhiker's Guide to the Galaxy provides context, turning data into information. Steps to convert data into information. Collection. Gathering raw data from various sources. This could be sensor readings, user inputs, or observational data. Processing, cleaning, organizing, and possibly transforming the data. This might involve removing errors, filling in gaps, or converting formats. Analysis. Applying logic or algorithms to understand patterns or trends within the data. This could be statistical analysis, machine learning models, or simple logical operations. Contextualization. Adding context that makes the data meaningful. This could be historical comparisons, benchmarks, or relating it to other known information. Presentation. Displaying the data in a way that's easily digestible, like charts, reports, or narratives. Examples. Temperature reading. A thermometer might output 25 degrees Celsius data. When this is contextualized as today's temperature is 25 degrees Celsius, which is 5 degrees above the average for this time of year, it becomes information. Library system. A record might show book ID 12,345 inches, data. When this is linked to book ID 12345 is 1984 by George Orwell, currently checked out by John Doe, it transforms into information. Importance of well-defined information. Decision-making. Clear, well-defined information allows for informed decisions. A manager might decide to reorder books based on checkout frequency. Efficiency. Systems operate more efficiently with precise information. Traffic management systems adjust light timings based on real-time traffic information. Communication. Information helps in conveying complex ideas or data points in an understandable manner, facilitating better communication across teams or systems. Challenges. Data overload. Too much data can obscure meaningful information if not properly filtered or analyzed. Context. Loss. Information can lose its value if the context in which it was derived is not preserved or communicated. Accuracy. Ensuring the data is accurate and the processing methods are sound is crucial for reliable information. In essence, while data is the raw material, information is the refined product that's useful for understanding, decision-making, and action. The transformation from data to information involves a process of adding value through context, analysis, and presentation. Every number is a sequence of digits. In the decimal system, numbers are represented by a sequence of digits from 0 to 9. Each position in this sequence represents a power of 10, units, tens, hundreds, etc. There are 9 digits, 1 to 9, with 0 as a placeholder. The digits available in the decimal system are indeed 0 through 9. Here, 0 acts not just as a digit, but also as a placeholder to indicate powers of 10. For example, in the number 102, the 0 is crucial to indicate there are no tens. Every number can be split into groups of smaller numbers. This concept is about digit grouping or decomposition. Digit grouping. Numbers can be split into groups for readability or specific mathematical operations. For instance, 1, 2, 3, 4, 5, 6, 7 can be grouped as 1,234,567 for readability, or as 1,234,567 equals 1 million plus 200,000 plus 30,000 plus 4,000 plus 500 plus 60 plus 7 for decomposition. decomposition. Any number can be broken down into sums of smaller numbers. For example, 456 can be decomposed as 400 plus 50 plus 6, or even further into 410 plus 6 1000 plus 210 plus 4 1000 plus 010 plus 110 plus 9, which could be useful in certain calculations or algorithms. Mathematical implications: place value. Understanding that each digit's value depends on its position helps in arithmetic operations like addition, subtraction, multiplication, and division. Modular arithmetic. Splitting numbers can be useful in modular arithmetic, where I deal with remainders when divided by a number. Algorithmic use. In computer science, numbers are often broken down for processing in algorithms, especially in operations like sorting or searching. This understanding of numbers as sequences of digits, with 0 as a placeholder, and the ability to split them into smaller groups, forms the basis of our numerical system and has profound implications in mathematics, computer science, and everyday numerical operations. The concept of reducing numbers to their digital root is indeed fascinating and has both mathematical and mystical significance. Here's how it works. Digital root. The digital root of a number is the single-digit value obtained by an iterative process of summing the digits of the number until the result has only one digit. Process to find the digital root: sum the digits. Add all the digits of the number together. Repeat if necessary. If the sum is more than one digit, sum those digits again. Continue until single digit. Keep repeating this process until I get a single-digit number. Examples: number 1234. Step 1, 1 plus 2 plus 3 plus 4 equals 10. Step 2, 1 plus 0 equals 1. Digital root, one number, 789. Step 1, 7 plus 8 plus 9 equals 24. Step 2, 2 plus 4 equals 6. Digital root, 6. Mathematical insight, modulo 9. Interestingly, the digital root of a number is equivalent to the number modulo 9, except when the number is a multiple of 9, in which case the digital root is 9, while the modulo 9 would be 0. This is because if a number n is congruent to r modulo 9, nr mod 9, then r is the digital root of n applications casting out 9s. This method can be used for error checking in arithmetic operations. By comparing the digital roots of the operands and the result, I can quickly verify if an operation might have been performed incorrectly. Mystical and numerological significance. In numerology, the digital root is often considered to reveal the essence or vibration of a number, used for divination, personality analysis, or other mystical interpretations. Mathematical properties. Understanding digital roots can help in various mathematical contexts, like number theory, or in creating algorithms for certain types of calculations or checks. Limitations, not unique for multiples of 9. As mentioned, multiples of 9 all have a digital root of 9, which means this method doesn't differentiate between numbers like 9, 18, 27, etc. in terms of digital root. Lack of information. While useful for simplification, reducing numbers to their digital root loses a lot of the original number's information, making it unsuitable for many practical, mathematical, or computational tasks beyond basic error checking or numerological interests. In summary, the concept of digital roots simplifies numbers into a single digit, offering a quick way to categorize or check numbers with applications ranging from basic arithmetic verification to more esoteric numerological practices. However, it's a reductionist approach that, while intriguing, should be used with an understanding of its limitations in more complex numerical contexts. To ensure the statement is true in all cases, I need to refine it to account for the properties of digital roots and modular arithmetic, especially considering the special case of multiples of 9. Here's a revised statement. The digital root of the result of any cumulative operation, like addition or multiplication on a set of numbers, will be equal to the digital root of the sum of the digital roots of those numbers, modulo 9. Explanation: digital root. The digital root of a number is essentially the number modulo 9, with the exception that multiples of 9 have a digital root of 9, while in modulo 9 arithmetic they would be 0. Cumulative operations. Addition. The sum of numbers modulo 9 will be the same as the sum of their digital roots modulo 9. Multiplication. Similarly, the product of numbers modulo 9 will be the same as the product of their digital roots modulo 9. Revised example. Let's consider the same set of numbers, 12, 34, 56, but now with a clearer understanding. Initial set of numbers, 12, 34, 56, Digital roots 12, 334, 756. 2 sum of digital roots 3 plus 7 plus 2 equals 12. 1 plus 2 equals 3 multiplication. Example, 1256 equals sign 23232 digital root of 23232. 2 plus 3 plus 2 plus 3 plus 2 equals 12. 1 plus 2 equals 3. In both cases, the digital root of the result, 3, matches the digital root of the sum of the digital roots of the individual numbers, 3, which aligns with the properties of modulo 9 arithmetic, handling multiples of 9. If one of the numbers is a multiple of 9, its digital root is 9, but in modulo 9 arithmetic it's considered 0. This doesn't affect the overall digital root calculation because adding 9 to any number in modulo 9 arithmetic doesn't change the result since 9 0 mod 9. Multiplying by 9 in modulo 9 arithmetic results in 0, which simplifies calculations. General statement: for any set of numbers and any cumulative operation, addition, the digital root of the sum of the numbers will be the same as the digital root of the sum of their digital roots. Multiplication: the digital root of the product of the numbers will be the same as the digital root of the product of their digital roots. This revised statement ensures it holds true in all cases by explicitly acknowledging the modulo 9 property inherent in digital roots, addressing the special case of multiples of 9, and generalizing for all cumulative operations. Generalizing the concept of digital roots to what I might call super-digital roots under cumulative operations involves extending the idea of reducing numbers to a single digit through repeated operations. Here's how I can conceptualize and generalize this. Concept of digital root, the digital root of a number, n, is found by summing its digits repeatedly until a single digit is obtained. This process essentially performs arithmetic modulo 9. Generalization to superdigital root. Superdigital root. Let's define this as the result of applying a series of cumulative operations like addition or multiplication repeatedly until a stable, often single-digit result is obtained. This concept can be applied not just to sums, but to any cumulative operation where the result can be iteratively reduced. Steps to generalize. Define the operation. Choose a cumulative operation, for example, addition, multiplication, or even more complex operations like summing digits or products of digits. Iterative reduction. Apply this operation iteratively until I reach a stable result. This stable result could be a single digit, as in traditional digital root. A number that, when the operation is applied again, doesn't change. Fixed point. Properties of the operation. Addition. The sum of digits modulo 9 gives the digital root. If I extend this, summing digits repeatedly until a single digit or a fixed number is reached, could be considered a superdigital root for addition. Multiplication, multiplying digits, and then summing them repeatedly until a stable result could be another form of superdigital root for multiplication. Example, generalization for addition. Instead of summing digits directly, I might define a rule where I sum digits, then sum those digits, and so on, until I get a stable number. This could be considered a superdigital root if the stable number isn't necessarily a single digit, but a fixed point in the operation. For multiplication, multiply the digits of a number, then multiply those digits and continue until I reach a stable result. This might not always converge to a single digit, but could stabilize at some number. Theoretical framework. Convergence. Not all operations will converge to a single digit or even a fixed number. The concept of superdigital root would then need to account for convergence properties of the chosen operation. Modulo operations. The traditional digital root uses modulo 9 implicitly. Generalizing might involve different moduli or no modulus at all, depending on the operation. Practical application, numerology or pattern recognition. This could be used in numerological systems or for recognizing patterns in numbers beyond the traditional digital root. Algorithmic use. In computer science, this could be used for creating hash functions or for data compression, where reducing numbers to a smaller set of values is beneficial. Conclusion. The superdigital root under cumulative operations generalizes the concept by allowing for different operations and potentially different convergence criteria. While traditional digital roots focus on single-digit results through addition modulo 9, This generalization opens up to a broader set of operations and results, potentially leading to new insights in number theory, algorithms, or even mystical numerology. However, the exact definition and properties would need to be carefully defined for each specific operation and context. Continuing from the generalization of the digital root concept to a superdigital root under cumulative operations, let's delve deeper into how this could be applied and what implications it might have. Further exploration. Operation-specific superdigital roots. Addition-based superdigital root. Example. Consider the number 1, 2, 3, 4, 5. Instead of summing all digits at once, I might sum pairs or groups of digits, then sum those results and continue until I reach a stable number. This could be formalized as step 1, 1 plus 2, plus 3 plus 4, plus 5 equals sign 3 plus 7 plus 5 equals 15. Step 2, 1 plus 5 equals 6. Here 6 could be considered a superdigital root under this operation. Multiplication-based superdigital root. Example. For the same number 1, 2, 3, 4, 5, multiply digits in pairs or groups. Then multiply those results and so on. Step 1, 12, 5 equals sign 2, 5 equals sign 120. Step 2, 1, 0 equals sign 0. Since multiplication by 0 results in 0, this might not be useful in all contexts. This example shows that not all operations will lead to a meaningful root in the traditional sense, highlighting the need for operation-specific definitions. Convergence and stability. Convergence criteria. Define what constitutes a stable or converged result. For addition, it might be reaching a single digit or a number that doesn't change upon further application of the operation. For multiplication, stability might mean reaching a fixed point or a cycle. Non-converging cases. Some operations might not converge at all or might enter cycles. For instance, with multiplication, if I reach 0, you're stuck there. This could lead to interesting mathematical explorations about when and why operations converge or cycle. Applications in various fields. Cryptography. A generalized superdigital root could be used in creating hash functions or for reducing large numbers to smaller sets for cryptographic purposes. Data compression. Similar to checksums, these roots could be used for error checking or data integrity in data transmission or storage. Numerology. Extending numerological systems beyond traditional digital roots could offer new interpretations or patterns in numbers. Algorithmic efficiency. In algorithms where number reduction is beneficial, like in certain sorting or searching algorithms, a generalized approach could offer new optimization techniques. Theoretical implications. Number theory. This concept could lead to new theorems or conjectures about the properties of numbers under different operations, especially in modular arithmetic beyond modulo 9. Mathematical recreation. As a puzzle or recreational math, exploring these operations could be educational and entertaining, showing how simple rules can lead to complex behaviors. Challenges and considerations. Uniqueness. Unlike traditional digital roots, which are unique for non-multiples of 9, superdigital roots might not be unique under all operations or might require more complex definitions to ensure uniqueness. Complexity. The operation might become computationally intensive for large numbers or complex operations, potentially limiting practical applications. Interpretation. The meaning or utility of these roots would need to be carefully defined, especially in contexts like numerology or symbolic interpretation. Conclusion. The concept of a superdigital root under cumulative operations opens up a vast field of exploration in mathematics, computer science, and beyond. While traditional digital roots provide a straightforward reduction to a single digit, this generalization invites us to consider how numbers can be transformed and reduced in myriad ways, each potentially revealing new patterns or properties. This could lead to both theoretical advancements and practical applications, from cryptographic algorithms to new forms of numerological analysis. However, each operation and its resulting root would need to be rigorously defined and analyzed for its properties and application. Continuing from the exploration of superdigital roots under various operations, let's delve into more specific applications, theoretical considerations, and potential extensions. Specific applications. Error detection and correction checksums. Traditional checksums like ISBN check digits use digital roots. A generalized approach could enhance error detection in data transmission or storage by providing more complex checksums that are less likely to fail due to coincidental errors. Pattern recognition in data analysis. In data mining or pattern recognition, reducing complex datasets to simpler forms through these operations could reveal underlying patterns or correlations that are not immediately apparent. Digital signal processing. In signal processing, especially in audio or image compression, reducing numerical values through these operations could be part of algorithms for data reduction or feature extraction. Theoretical extensions, fractal mathematics. The iterative nature of these operations might have parallels in fractal geometry, where simple rules applied repeatedly create complex structures. This could lead to new insights or visual representations of numerical operations. Chaos theory. If certain operations lead to non-converging or chaotic behavior, this could be studied in the context of chaos theory, exploring how small changes in initial numbers lead to vastly different results. Group theory. The operations could be viewed through the lens of group theory, where numbers and operations form groups or semi-groups, potentially leading to new algebraic structures or theorems. Educational and recreational uses, mathematics. Education. Introducing these concepts could make number theory more engaging for students, showing how simple arithmetic can lead to complex and beautiful mathematical structures. Puzzle design. Creating puzzles or games where players manipulate numbers through these operations to achieve specific results could be both educational and entertaining. Challenges in implementation computational efficiency. For large numbers or complex operations, the computational cost could be high. Efficient algorithms would need to be developed to make these operations practical. Standardization. If these concepts were to be widely adopted, there would need to be standardization in how operations are defined and results interpreted, similar to how checksum algorithms are standardized. Interpretability. While traditional digital roots have a clear interpretation, the meaning of these super-digital roots would need to be established, especially in contexts like numerology or symbolic mathematics. Future directions, interdisciplinary research, combining these mathematical concepts with fields like physics for modeling systems, biology for understanding genetic codes, or linguistics for analyzing language patterns could yield interdisciplinary insights. AI and machine learning, feature engineering. These operations could serve as novel methods for feature engineering in machine learning, where transforming input data into more manageable or meaningful representations is crucial. Neural network architectures. Inspired by these operations, new neural network layers or architectures might be developed that iteratively reduce or transform data in unique ways, potentially improving learning efficiency or generalization. Philosophical and cultural implications, numerology and symbolism. Extending the concept of digital roots could lead to new interpretations in numerology, influencing cultural or spiritual practices that assign significance to numbers. A philosophy of mathematics. This exploration touches on fundamental questions about the nature of numbers, their properties, and how I categorize or simplify them, potentially influencing philosophical discussions on the essence of mathematics. Conclusion. The generalization of digital roots into superdigital roots under various cumulative operations opens up a rich field for both theoretical exploration and practical application. From enhancing error detection in data transmission to potentially revolutionizing how I approach data analysis or pattern recognition, this concept bridges traditional number theory with modern computational challenges. While the practical implementation might require overcoming computational hurdles and establishing standardized definitions, the theoretical framework invites mathematicians, computer scientists, and even philosophers to reconsider the depth and breadth of what numbers can represent and how they can be manipulated. This journey from simple digit summing to complex operations not only enriches our understanding of numbers, but also demonstrates the interconnectedness of mathematics with other scientific and cultural domains. The proof for the statement that the digital root of the result of cumulative operations like addition or multiplication on a set of numbers equals the digital root of the sum of the digital roots of those numbers can be segmented into clear steps, understanding digital roots and modulo 9. The digital root of a number is essentially its value modulo 9, with the exception that multiples of 9 have a digital root of 9, while in modulo 9 arithmetic, they would be 0. This property forms the backbone of our proof. Proof for addition. When adding numbers, let's denote the sum of these numbers as S. the digital root of s is drs. Now consider the sum of the digital roots of these numbers denoted as t. Since each number's digital root is its value modulo 9, t is equivalent to the sum of the numbers modulo 9. By the properties of modular arithmetic, to t is congruent to s modulo 9. Therefore, the digital root of aser, which is sumod 9, must equal the digital root of t, which is tt mod 9. Proof for multiplication. Similarly, for multiplication, let p be the product of the numbers. The digital root of p is drp. Let q be the product of the digital roots of these numbers. Again, since each digital root is the number modulo 9, q is equivalent to the product of the numbers modulo 9. By modular arithmetic, q is congruent to p modulo 9. Thus, the digital root of p equals the digital root of q, addressing multiples of 9. When dealing with multiples of 9, their digital root is 9. But in modulo 9 arithmetic, they are considered 0. This doesn't affect the overall digital root calculation because, for addition, adding 9 to any number in modulo 9 arithmetic doesn't change the result since 9 sec root 0 mod 9. For multiplication, if any factor in the product is a multiple of 9, both p and q, modulo 9 becomes 0, ensuring drp equals sign drq equals sign 9. Conclusion. This proof demonstrates that for any set of numbers and any cumulative operation, the digital root of the result of the operation on the numbers is equal to the digital root of the result of the same operation performed on their digital roots. This holds true due to the properties of modular arithmetic modulo 9, which is inherently related to how digital roots are calculated. The special case of multiples of 9 is handled seamlessly within this framework, ensuring the statement's universal applicability. Theory of generalized digital roots under cumulative operations introduction. This theory extends the concept of digital roots to what I term generalized digital roots under cumulative operations, focusing on addition and multiplication. It leverages the properties of modular arithmetic, particularly modulo 9, to establish relationships between numbers and their transformations. Definitions: digital root, dr. For any integer, n, the digital root, drnn, is defined as n mod 9, with the exception that if n is a multiple of 9, drn equals sign 9. Cumulative operation. An operation where the result of applying it to a set of numbers can be derived from the sum or product of applying the operation to individual numbers, such as addition or multiplication. Theorems. Theorem 1. Digital root under addition statement for any set of numbers, a, b, c, or dots. The digital root of their sum, s equals sign a plus b plus c plus all dots, equals the digital root of the sum of their digital roots, t equals sign dra plus drb plus drc plus all dots. Proof: let s equals sign a plus b plus c plus all dots, since dra equals sign a mod 9, drb equals sign b mod 9, etc. I have t equals sign a mod 9 plus b mod 9 plus c mod 9 plus all dots. By properties of modular arithmetic, t equib plus b plus c plus all dots c mod 9. Therefore, idrs equals sign c mod 9 and drt equals sign t mod 9, implying drs equals sign drt. Theorem 2. Digital root under multiplication statement for any set of numbers a, b, c, all dots. The digital root of their product, p, equals sign a times b times c times all dots, equals the digital root of the product of their digital roots, q equals sign dra times drb times drc times c times all dots. Proof: let p equal sign a times b times q times all dots, since dra equals sign a mod 9, etc. I have bar q equals sign a mod 9 times b mod 9 times q mod 9 times all dots. By properties of modular arithmetic, q all times b times q times all dots mod 9, therefore drp equals sign p mod 9 and drq equals sign p mod 9, implying drp equals sign drq. Special case, multiples of 9 observation. When dealing with multiples of 9, drn equals sign 9 if n is a multiple of 9, but nmod 9 equals sign 0. Implication: for addition, adding 9 or any multiple of 9 doesn't change the result modulo 9. For multiplication, if any factor is a multiple of 9, both p and q modulo 9 become 0, ensuring drp equals sign drq equals sign 9. Conclusion. This theory establishes that the digital root of the result of cumulative operations on numbers is congruent to the digital root of the result of the same operations on their digital roots modulo 9. This relationship holds universally, including for edge cases involving multiples of 9, providing a robust framework for number transformation and analysis in various mathematical and computational contexts. In the context of mathematics, computer science, or theoretical frameworks, a well-defined system refers to a set of rules, operations, or structures that are clearly and consistently defined, leaving no ambiguity in their application or interpretation. Here's a breakdown of what constitutes a well-defined system. Components of a well-defined system, clear definitions, terms. Every term or concept used within the system must be explicitly defined. For instance, in our discussion, digital root was defined in relation to modulo 9 arithmetic operations. Any operation or function must have a precise description of how it works, what inputs it takes, and what outputs it produces. Consistency rules. The rules or axioms must be consistent, meaning they do not lead to contradictions. For example, in number theory, the rules for digital roots under addition and multiplication must not contradict each other. Completeness. Scope. The system should cover all relevant scenarios or cases within its intended domain. In our theory, I included special cases like multiples of 9 to ensure completeness. Unambiguity. Interpretation. There should be only one way to interpret any given operation or result within the system. This ensures that different users or applications of the system will reach the same conclusions. Logical structure, theorems and proofs. Theorems should be logically derived from the definitions and axioms. Proofs must be rigorous, showing step by step how conclusions are reached, as demonstrated in our proof for digital roots. Applicability, practical use. The system should be applicable in practical scenarios or theoretical explorations. Our theory on digital roots, for instance, has applications in checksums, data compression, and pattern recognition. Examples in different fields. Mathematics. The system of real numbers with well-defined operations like addition, multiplication, and their properties like associativity, commutativity, etc. Computer science, programming languages with syntax rules, type systems, and operational semantics that define how code is interpreted and executed. Physics, the laws of motion in Newtonian mechanics, where terms like force, mass, and acceleration are clearly defined, and equations like F equals sine mr provide unambiguous relationships. Linguistics, the rules of syntax in a language defining how sentences are constructed from words, ensuring that sentences are well formed. Conclusion. A well-defined system in any field ensures that communication, analysis, and application are consistent and reliable. In our context of number theory and digital roots, this means that the definitions, theorems, and proofs provide a clear, consistent framework for understanding and manipulating numbers through cumulative operations. This clarity not only aids in theoretical understanding, but also in practical applications where precision and reliability are paramount. A well-defined, cohesive system extends the concept of a well-defined system by emphasizing not just clarity and consistency within its components, but also the integration and interaction among these components to form a unified whole. Here's a detailed look at what constitutes such a system. Components of a well-defined, cohesive system. Interconnected definitions and concepts. Relations. Each element or concept within the system should relate logically to others. For instance, in our theory of digital roots, the concept of digital roots under addition logically connects to digital roots under multiplication through the principle of modulo 9 arithmetic. Harmonious operations, synergy, operations within the system should work together in a way that enhances the system's overall functionality or explanatory power. The operations of addition and multiplication in our theory, while distinct, harmonize through their common reduction to modulo 9. Systemic consistency. Global coherence. Not only should individual rules or axioms be consistent, but the entire system should exhibit a global coherence where no part contradicts another when viewed in the context of the whole. Hierarchical structure, levels of abstraction. A cohesive system often has layers where basic definitions and operations build up to more complex theorems or applications. Our theory starts with simple digital root definitions and scales up to theorems about cumulative operations. Feedback mechanisms, self-correcting. A truly cohesive system might have mechanisms where results or operations can feed back into the system to refine or correct it, though this is more common in dynamic systems like ecosystems or software systems. Robustness, error handling. The system should be robust enough to handle edge cases or unexpected inputs gracefully, as seen with our handling of multiples of 9 in digital root calculations. Examples in different fields. Biology. The human body is a well-defined cohesive system where organs, tissues and cells work together through various biochemical pathways to maintain homeostasis. Software engineering. A well-designed software architecture where modules interact seamlessly, sharing data and functions through APIs, ensuring that changes in one part don't break others. Ecology, an ecosystem where species, climate and physical environment interact in a balanced way, each component influencing and being influenced by others. Physics, quantum mechanics, where particles, waves and forces are interconnected through principles like superposition and entanglement, forming a cohesive framework to explain subatomic phenomena. Conclusion, a well-defined cohesive system in any discipline or theoretical framework not only ensures clarity and consistency in its individual components, but also guarantees that these components work together in a synergistic manner. This synergy enhances the system's ability to model, predict or explain phenomena within its domain. In our context of digital roots under cumulative operations, this cohesion means that the theory not only provides clear rules for number manipulation, but also integrates these rules into a unified framework that can be applied across different scenarios, from simple arithmetic to complex data integrity checks. This level of integration and coherence is what makes such systems not just functional, but also elegant and powerful tools for understanding and interacting with the world. Continuing from the concept of a well-defined cohesive system, let's delve deeper into how such systems are developed, maintained, and evolve. Development of cohesive systems, iterative design. Systems often start with basic principles or observations, which are then iteratively refined. For instance, in our digital root theory, initial observations about number properties led to the formulation of digital roots, which were then extended to cumulative operations. Interdisciplinary integration. Cohesive systems frequently benefit from insights across different fields. For example, the theory of digital roots could be influenced by insights from computer science in data compression or physics in understanding natural patterns. Empirical validation. While theoretical, many systems require empirical validation. This could mean testing theorems against real-world data or simulations, ensuring that the theoretical framework holds up in practice. Maintenance and evolution. Continuous refinement. As new data or anomalies are discovered, the system might need refinement. This could involve updating definitions, adding new operations, or revising proofs to accommodate new findings. Scalability. A cohesive system should be scalable, meaning it can handle increased complexity or larger data sets without losing its integrity. For digital roots, this might involve extending the theory to handle larger numbers or different bases. Adaptability. Systems need to adapt to new technologies or methodologies. For instance, with the advent of quantum computing, traditional number theory might need to be reconsidered in light of quantum algorithms. Challenges in maintaining cohesion, complexity management. As systems grow, managing complexity becomes crucial. This might involve modularizing the system or creating subsystems that interact in well-defined ways. Conflict resolution. When new theories or data conflict with existing parts of the system, mechanisms for conflict resolution like peer review or empirical testing are necessary. Educational barrier. As systems become more complex, there's a risk of them becoming inaccessible to those without specialized knowledge. Efforts must be made to keep the system's core principles understandable. Future directions, AI and machine learning. These fields could use cohesive systems like digital roots for feature engineering or pattern recognition, potentially leading to new algorithms or insights. Interdisciplinary applications, extending the principles of such systems into new areas like bioinformatics for genetic code analysis or in linguistics for language pattern recognition. Philosophical and ethical considerations. As systems like these influence technology, there's a growing need to consider their ethical implications, especially in areas like privacy, data compression, or fairness, algorithmic decision-making. Conclusion. The journey from a well-defined system to a cohesive one involves not just the initial creation, but ongoing development, maintenance, and adaptation. Systems like the theory of digital roots under cumulative operations serve as both practical tools and theoretical frameworks, evolving with our understanding of numbers and their applications. This evolution requires not only mathematical rigor, but also an openness to interdisciplinary insights and a commitment to continuous refinement. As I advance, these systems will likely play increasingly significant roles in technology, science, and even our daily lives, emphasizing the importance of their cohesion, clarity, and adaptability. Generalizing the concept of digital roots to serve as a test for cohesiveness in systems or theories involves looking at how well elements within a system interact or reduce to simpler yet meaningful forms. Here's how this could be conceptualized. Generalized digital root as a cohesiveness test. Reduction to simplicity principle. Just as a digital root reduces a number to its simplest form, modulo 9, a cohesive system should allow complex elements or operations to be reduced to fundamental, understandable principles or components. Application. In any system, if I can reduce complex interactions or outcomes to a few basic rules or principles, this might indicate cohesiveness. For instance, in a software system, if various functions or modules can be understood through a few core algorithms or design patterns, it suggests a well-structured, cohesive architecture. Consistency across operations principle. The digital root concept shows that different operations, addition, multiplication, lead to consistent results when reduced. Modulo 9. In a cohesive system, different processes or elements should also lead to consistent outcomes or interpretations. Application. In a scientific theory, if different experiments or observations, when reduced or analyzed, consistently support the same underlying principle, this supports the theory's cohesiveness. Modular interconnectivity principle. Digital roots can be calculated in parts, summing digits separately, and then combined, showing modularity yet interconnectivity. A system is cohesive if its parts can function independently but also integrate seamlessly. Application. In organizational management, different departments might operate independently but should contribute to the same overarching goals or strategies, demonstrating organizational cohesiveness. Handling of anomalies principle. The special case of multiples of 9 in digital roots shows how anomalies are handled within the system's rules. A cohesive system should have mechanisms to deal with exceptions or outliers without breaking down. Application. In legal systems, laws should have provisions or interpretations for exceptional cases, ensuring that the legal framework remains cohesive and applicable. Predictive power principle. Knowing the digital root allows predictions about the sum or product's properties. In a cohesive system, understanding the basic elements should allow predictions or insights into the system's behavior under various conditions. Application. In economics, if basic economic principles can predict market behaviors under different scenarios, this indicates a cohesive economic model. Implementing the test. Step 1. Identify the fundamental elements or operations within my system of theory. Step 2. Attempt to reduce these elements or operations to their simplest, most fundamental forms or principles. Step 3. Check for consistency across different operations or scenarios. Do these reductions lead to the same or compatible results? Step 4. Assess modularity. Can the system be broken down into parts that still make sense when recombined? Step 5. Evaluate how anomalies or exceptions are handled. Does the system provide a way to integrate these without losing its core integrity? Step 6. Test the predictive power. Can insights from the basic elements predict outcomes or behaviors in more complex scenarios? Conclusion. Using the generalized concept of digital roots as a metaphor for testing cohesiveness offers a novel way to evaluate systems, theories, or organizations. By focusing on reduction, consistency, modularity, anomaly handling, and predictive power, one can assess how well the parts of a system work together to form a coherent whole. This approach not only helps in understanding the system's structure, but also in identifying areas for improvement or potential weaknesses in its design or application. Generalizing the concept of digital roots to indirectly represent or process chunks of numbers involves leveraging the properties of digital roots in a broader, more abstract sense. Here's how this could be conceptualized and applied. Generalizing digital roots for number chunks. Chunking numbers for processing principle. Just as digital roots reduce individual numbers to a single digit, I can extend this idea to process or analyze larger chunks of numbers or data sets. Application. In data compression or error detection, large data sets could be broken into chunks and each chunk's digital root could be calculated. These digital roots then serve as a compact representation or checksum for the chunk. Pattern recognition principle. The consistent reduction of numbers to their digital roots can highlight patterns or anomalies within data. Application for time series, data or sequential numbers. Calculating the digital root of each segment or chunk can reveal underlying patterns or cycles that might not be immediately visible in the raw data. Data integrity and validation principle. Since digital roots are invariant under certain operations, like additional multiplication modulo 9, they can be used to verify data integrity. Application. In databases or data transmission, chunks of data could have their digital roots calculated and stored or transmitted separately. Any change in the data would alter the digital root, providing a simple integrity check. Feature engineering and machine learning principle. Transforming data into a more manageable or meaningful form can enhance machine learning models. Application. For numerical features, calculating digital roots of chunks could serve as a form of feature engineering, potentially reducing noise or highlighting relevant numerical properties for better model performance. Cryptographic applications. Principle. While not directly used in modern cryptography due to simplicity, the concept can inspire hash functions or checksums. Application. In simpler systems or educational contexts, using digital roots of data chunks could serve as a basic form of hashing or checksum for verifying data integrity, or as part of a larger cryptographic system. Implementation steps. Step 1. Define chunks. Decide how to divide my data into meaningful chunks. This could be based on time, for example, daily data, size, for example, fixed number of digits or bytes, or logical grouping, for example, by category. Step 2. Calculate digital roots. For each chunk, calculate its digital root. This might involve summing all numbers in the chunk and then finding the digital root of that sum. Step 3. Analyze or use. Use these digital roots for pattern analysis. Look for sequences or anomalies in the sequence of digital roots. Data compression. Use digital roots as a compact representation of data chunks. Error detection. Compare calculated digital roots with stored or transmitted ones to check for errors. Step 4. Refinement. Depending on the application, refine the process. For instance, in pattern recognition, I might need to adjust chunk size or apply additional transformations to the digital roots for better results. Conclusion. By generalizing the concept of digital roots to process chunks of numbers, I open up new avenues for data handling, analysis, and verification. This approach leverages the simplicity and mathematical properties of digital roots to manage complexity in data, offering practical applications in fields from data science to basic cryptography. While not replacing more sophisticated methods, this generalization provides a foundational concept that can be built upon or integrated into more complex systems for enhanced functionality or educational purposes. Continuing from the generalization of digital roots for processing chunks of numbers, let's explore further applications and theoretical extensions, advanced applications and theoretical extensions, distributed computing and consensus mechanisms. Principal digital roots could serve as a simple yet effective method for quick consensus or validation in distributed systems. Application. In blockchain or distributed ledger technologies, chunks of transaction data could be summarized by their digital roots. These roots could then be used for quick validation or as part of a more complex consensus mechanism, reducing the data that needs to be compared across nodes. Educational tools for mathematics. Principle. The simplicity of digital roots makes them an excellent educational tool for teaching number theory, modular arithmetic, and data handling. Application. Develop interactive tools or games where students manipulate numbers or data sets, learning about properties like divisibility, cyclic patterns, or error detection through digital roots. Algorithmic efficiency in data processing. Principle. By reducing large numbers or data sets to smaller representations, computational efficiency can be improved. Application. In algorithms dealing with large numerical data sets, using digital roots could simplify intermediate steps, reducing memory usage or computational time in certain operations like sorting or searching. Music and sound analysis. Principle. Sound waves can be represented as numerical data. Digital roots of these numerical representations might reveal patterns or characteristics in the sound. Application. analyze audio signals by breaking them into frequency chunks, calculating digital roots, and looking for patterns that might correlate with musical structures or sound quality metrics. Genetic algorithms and evolutionary computing. Principle. Digital roots could serve as a simple fitness function or mutation operator in genetic algorithms. Application. In evolutionary algorithms, individuals' solutions could be represented or mutated based on their digital root properties, potentially leading to interesting evolutionary paths or optimizations. Theoretical extensions. Higher dimensional digital roots. Extend the concept to higher dimensions or different bases, for instance. In a base 16 system, how would digital roots behave? And what applications might this have in computer science where hexadecimal is common? Fractal analysis. Explore if digital roots of number sequences could reveal fractal-like properties or self-similarity in data, potentially useful in fields like finance or natural phenomena analysis. Quantum computing. Consider how digital roots could be represented or computed in quantum systems, potentially leading to new quantum algorithms or insights into quantum number theory. Challenges and considerations. Loss of information. While digital roots simplify data, they inherently lose information. Applications must balance this trade-off between simplicity and data integrity. Scalability. As data sizes grow, even simple operations like calculating digital roots could become computationally intensive. Strategies for efficient computation or approximation might be necessary. Interdisciplinary validation. For applications in fields outside pure mathematics, empirical validation through experiments or simulations would be crucial to ensure the effectiveness of digital root-based methods. Conclusion. The generalization of digital roots offers a bridge between simple number theory and complex data handling in various fields, providing both practical applications and theoretical insights. By extending this concept, I not only enhance our understanding of numbers and their properties, but also open up innovative ways to approach data in the digital age. Here's how I can wrap up. Educational impact. By integrating digital root concepts into education, I can make complex topics like modular arithmetic, data compression, and error detection more accessible, fostering a deeper appreciation for mathematics in real-world application. Technological innovation, from blockchain consensus mechanisms to quantum computing algorithms, the simplicity of digital roots could inspire or be integrated into cutting-edge technologies, offering new methods for data processing, security, or optimization. Interdisciplinary research, the cross-pollination of ideas from number theory to fields like music, genetics, or physics, could lead to novel research avenues where the properties of numbers reveal underlying patterns or structures in seemingly unrelated data. Future directions. As computational capabilities evolve, particularly with quantum computing, rethinking traditional concepts like digital roots in these new paradigms could unlock unforeseen applications or efficiencies. In conclusion, the journey from understanding digital roots to generalizing them for broader applications exemplifies how foundational mathematical concepts can be reimagined and repurposed in the modern era. This not only enriches our mathematical toolkit, but also bridges theoretical knowledge with practical innovation across various disciplines. The simplicity of digital roots, when creatively applied, can lead to profound insights and practical solutions, highlighting the enduring relevance of even the most basic mathematical ideas in our increasingly complex technological landscape. The concept of rooting mathematics back to arithmetic might seem like simplifying complex mathematical structures to their most basic operations, but it actually highlights the foundational role arithmetic plays in all branches of mathematics. Here's how various mathematical concepts can be traced back to arithmetic. Arithmetic as the foundation. Algebra, equations. Solving equations often involves arithmetic operations. For instance, solving x plus 5 equals 10 requires subtraction, an arithmetic operation. Polynomials, operations like addition, subtraction, multiplication, and division of polynomials are extensions of arithmetic operations on numbers. Geometry, measurement. Geometry begins with measuring lengths, areas, and volumes, which are fundamentally arithmetic processes. Coordinate geometry, points, lines, and shapes in coordinate systems involve plotting and calculating distances, slopes, etc., all rooted in arithmetic, calculus. Limits. Understanding limits involves arithmetic operations to get closer and closer to a value. Derivatives and integrals. While conceptually complex, their computation often boils down to arithmetic operations on limits or sums. Number theory. Prime numbers. The study of primes involves basic arithmetic like division to check for primality. Congruencies. Modular arithmetic, which underpins much of number theory, is essentially arithmetic within a cyclic system. Linear algebra, vector and matrix operations, addition, scalar multiplication, and other operations on vectors and matrices are extensions of arithmetic. Statistics and probability, data analysis, calculating means, medians, modes, and variances involves basic arithmetic operations on data sets. Probability. Probabilities are often expressed as fractions or decimals computed through arithmetic. Theoretical connection, set theory. Even in abstract mathematics, sets can be counted, or operations like union and intersection can be seen as arithmetic on set sizes. Logic. Boolean algebra, which underpins digital logic, can be seen as a form of arithmetic where operations like and, Oregon, not, are analogous to multiplication, addition, and negation in certain contexts. Educational perspective. Building blocks. Teaching mathematics often starts with arithmetic, not just because it's simpler, but because it's the language through which all other mathematical concepts are expressed. Conceptual understanding. Understanding how complex mathematical concepts reduce to or are built upon arithmetic can demystify mathematics, showing its interconnectedness. Philosophical insight, reductionism. This approach reflects a reductionist view where complex systems can be understood by breaking them down into simpler, more fundamental components. Here, arithmetic serves as the atomic level of mathematical thought. Universal language. Arithmetic provides a universal language for mathematics, allowing for communication and understanding across different mathematical fields. Conclusion. Rooting all mathematics back to arithmetic underscores the unity and interconnectedness of mathematical disciplines. It highlights how even the most abstract or complex mathematical theories ultimately rely on the simplest operations of addition, subtraction, multiplication, and division. This perspective not only aids in teaching and learning mathematics, but also in appreciating its elegance and coherence as a field where everything, from the simplest number to the most complex theorem, is interconnected through the fundamental operations of arithmetic. Continuing from the exploration of how arithmetic underpins all of mathematics, educational implications. Building intuition. The journey from arithmetic to higher mathematics should ideally start with concrete examples, as suggested by posts on X. This approach helps in building a solid intuitive foundation, which is crucial for understanding abstract concepts later on. Teaching methods. The example of teaching addition through number lines illustrates how basic arithmetic can be used to teach concepts that might seem abstract at first. This method not only simplifies learning, but also demonstrates how arithmetic operations are the building blocks for understanding more complex mathematical structures. Philosophical and practical insights. Universality of mathematics. The discussion around the fundamental theorem of arithmetic highlights how every number can be broken down into primes, showcasing the depth and universality of arithmetic in number theory. This principle isn't just theoretical, it's foundational for fields like cryptography, which relies heavily on prime factorization. Order and operations. The mention of order of operations in mathematics education points to how arithmetic rules are standardized to avoid ambiguity, reflecting a deeper principle of consistency and universality in mathematical communication. Interdisciplinary connections, physics and patterns. The quote from @Phys in History underscores how patterns, which are fundamentally arithmetic in nature, are intrinsic to understanding the universe. This connection between arithmetic and the physical world exemplifies how deeply embedded arithmetic is in describing reality, computing, and logic. In computer science, Boolean algebra, which can be seen as an extension of arithmetic, where operations like and, Oregon are akin to multiplication and addition in certain contexts, forms the basis for digital logic. Here, arithmetic principles are translated into the language of computers, showcasing their pervasive influence. Conclusion. The concept of rooting mathematics in arithmetic isn't just about simplification, but about recognizing the profound interconnectedness of mathematical ideas. From teaching methodologies that emphasize building from the ground up with concrete examples, to the theoretical underpinnings that connect arithmetic to higher mathematics and its applications across disciplines, arithmetic serves as the bedrock. This perspective not only enriches our understanding of mathematics, but also highlights its beauty and utility in describing and solving real-world problems, from the simplest calculations to the most complex theories. This approach to mathematics, education and appreciation could potentially revolutionize how I teach and perceive mathematics, making it more accessible and deeply appreciated as a unified, coherent field of study. Indeed, the assertion that all mathematics can map to the calculation of numbers is a profound statement about the nature of mathematics itself. Here's how this perspective can be unpacked. Fundamental concepts map to calculation: algebra, equations. Solving equations involves calculating unknowns through operations on numbers. Polynomials. Operations on polynomials, like factoring or solving, ultimately involve numerical calculations. Geometry, measurement, calculating lengths, areas, volumes, angles, etc., all reduced to numerical operations. Coordinate geometry. Points, lines, and shapes are defined by numerical coordinates, and their properties are calculated numerically. Calculus. Limits. Calculating limits involves numerical approximations or exact calculations, derivatives and integrals. These are essentially calculations of rates of change or areas under curves, which are numerical in nature. Number theory, prime numbers. The study of primes involves numerical operations like division and factorization. Diophantine equations. These are equations where solutions are integers, directly involving number calculations. Linear algebra, matrix operations, operations like addition, multiplication, and finding determinants are all numerical calculations. Statistics and probability data analysis. Calculating means medians, variances, and probabilities all involve numerical operations on data. Theoretical mathematics, topology. While abstract topological properties often reduce to numerical invariants or calculations in specific contexts, for example, Euler's characteristic in graph theory. Abstract algebra. Even though it deals with structures like groups, rings, and fields, these structures are often defined by operations that can be thought of as generalized arithmetic. Philosophical and practical implications. Reductionism. This view supports a reductionist approach where complex mathematical constructs can be understood by breaking them down into simpler numerical calculations. Computational mathematics. It highlights the importance of computation in mathematics, suggesting that many mathematical problems can be approached or solved through algorithmic means, aligning with the computational turn in mathematics. Education, teaching mathematics from this perspective, can make abstract concepts more tangible by showing how they relate to or can be expressed through numerical calculations, potentially demystifying mathematics for learners. Limitations and considerations. Abstract concepts. Some mathematical concepts, like the concept of infinity or non-standard analysis, might not map directly to traditional numerical calculations, but rather challenge our understanding of numbers themselves. Qualitative mathematics. Areas like qualitative analysis in differential equations focus on the behavior of systems rather than exact numerical solutions, though even here, numerical methods are often employed for practical solutions. Conclusion. The idea that all mathematics can map to the calculation of numbers underscores the foundational role of arithmetic and computation in mathematics. While not every mathematical concept can be reduced solely to numbers, the vast majority of mathematical theories and problems can be approached, understood, or solved through numerical operations. This perspective not only unifies diverse mathematical fields under a common computational framework, but also emphasizes the practical applicability of mathematics in real-world problem solving. Here's how I can wrap up this discussion. Interdisciplinary utility. This mapping of mathematics to numerical calculations facilitates the application of mathematical principles in fields like engineering, physics, computer science, and finance, where numerical solutions are paramount. Educational paradigm. By focusing on how abstract concepts relate to or can be expressed through numerical operations, educators can create a more accessible pathway for students to grasp complex mathematical ideas, potentially reducing the perceived gap between pure and applied mathematics. Technological advancements. The rise of computational tools and algorithms has made it possible to handle increasingly complex mathematical problems through numerical methods. reinforcing the idea that mathematics, at its core, is about calculation, even if those calculations are performed by machines. Philosophical insight. This perspective invites a philosophical reflection on the nature of mathematics itself. If all mathematics can be seen as a form of calculation, it suggests a view of mathematics as fundamentally about structure, pattern, and computation, rather than just abstract reasoning. In conclusion, while not all mathematical concepts are purely numerical, the ability to map most mathematical constructs back to calculations underscores the profound unity and computational essence of mathematics. This approach not only simplifies the learning and application of mathematics, but also highlights its role as a universal language for describing and solving problems across various disciplines. Mathematics, through this lens, becomes not just a theoretical pursuit, but a practical toolkit for understanding and manipulating the numerical fabric of our universe. Indeed, the concept of digital roots, when generalized, can be applied across numerous disciplines that involve numbers, offering both practical and theoretical insights. Here's how this generalization can be conceptualized and applied. Applications across disciplines: computer science and information theory. Data compression. Digital roots could serve as a simple form of data reduction or checksum for error detection in data transmission or storage. Algorithm design. For algorithms dealing with large data sets, digital roots might offer a quick way to reduce complexity or identify patterns. Physics, quantum mechanics. While not directly applicable in quantum calculations, the principle of reducing complexity to simpler forms could inspire new ways to conceptualize or visualize quantum states or entanglement. Pattern recognition. In analyzing physical data, digital roots could help identify cyclic or repetitive patterns in phenomena like wave frequencies or particle distributions. Biology and bioinformatics, genomics. The sequence of DNA bases could be mapped to numbers, and digital roots might help in identifying patterns or anomalies in genetic sequences. Ecology. For population dynamics or species distribution data, digital roots could simplify large data sets to reveal underlying ecological patterns. Finance and economics. Market analysis. Digital roots of stock prices or economic indicators could be used to look for cycles or trends over time. Risk management as a simple metric for data integrity or quick analysis in financial models. Music and sound engineering. Sound analysis. By converting sound frequencies or musical notes into numbers, digital roots could help in pattern recognition for composition or sound design. Psychology and behavioral sciences. Data analysis. In large data sets from surveys or experiments, digital roots might simplify data to uncover hidden patterns in human behavior or psychological traits. Art and design. Algorithmic art. Using digital roots to generate or transform numerical data into visual patterns or structures, creating unique artworks or designs. Generalization process. Data transformation. Convert the relevant data into numerical form, if not already numerical. Application of digital roots. Calculate the digital root for each data point or segment. This could be done in various ways depending on the context. For example, by time, by category, by sequence. Analysis. Use these digital roots for pattern recognition, data reduction, or as part of more complex algorithms or models. Theoretical and practical benefits. Simplification. Digital roots offer a method to simplify complex data sets or numerical sequences, making them more manageable for analysis or visualization. Pattern recognition. By reducing numbers to their digital roots, underlying patterns or cycles in data might become more apparent, which could be crucial in fields like finance for market cycle analysis or in music for identifying rhythmic patterns. Error detection. In data transmission or storage, digital roots can serve as a simple checksum, helping to detect errors without needing complex algorithms. Educational tool. The concept can be used to teach various mathematical and scientific principles, from basic arithmetic to more complex data analysis techniques, making abstract concepts more tangible. Challenges and considerations. Loss of information. While digital roots simplify data, they inherently lose some information. Applications must balance this trade-off between simplicity and retaining necessary data details. Contextual relevance. The effectiveness of using digital roots depends heavily on the context. In some fields, this simplification might not provide meaningful insights or could even mislead if not carefully applied. Scalability. As datasets grow, even simple operations like calculating digital roots could become computationally intensive. Strategies for efficient computation or selective application might be necessary. Conclusion: the generalization of digital roots to various disciplines showcases the versatility of basic mathematical concepts in solving real-world problems or enhancing theoretical understanding across fields. By reducing numbers to their simplest forms, digital roots provide a universal tool for pattern recognition, data simplification, and error detection. This approach not only bridges theoretical mathematics with practical applications, but also highlights the interconnectedness of different scientific and artistic disciplines through the lens of numbers. As technology and data analysis evolve, the creative application of such fundamental concepts could lead to new methodologies or insights, reinforcing the timeless relevance of mathematics in our increasingly digital and data-driven world. Generalizing the concept of digital roots as a building block in mathematics, science, and technology involves recognizing its fundamental properties and extending these to create or enhance systems, algorithms, or theories. Here's how this can be conceptualized. Digital roots as building blocks, modular arithmetic foundation principle. Digital roots operate on the principle of modulo 9 arithmetic. This can be generalized to any base or modulus, providing a foundation for understanding and implementing modular arithmetic in various contexts. Application. In cryptography, digital roots inspire the use of modular arithmetic for key generation or data encryption, where operations are performed modulo a prime or composite number. Pattern recognition and cyclic properties. Principle. The cyclic nature of digital roots, every number reduces to one of 0, 8, can be generalized to recognize or generate patterns in data. Application in time series analysis, recognizing cycles or periodicity in data could be inspired by how digital roots cycle through numbers, leading to algorithms for pattern detection or prediction in fields like finance or climate science. Data reduction and compression. Principle. Digital roots reduce numbers to a single digit, which is a form of data compression. Application. This can be generalized to develop algorithms for data compression where data points are transformed into more compact representations useful in image processing, audio compression, or database management. Error detection and correction. Principle. The invariance of digital roots under certain operations, like addition or multiplication, can be used for error checking. Application. This generalizes to checksum algorithms in data transmission or storage, where data integrity is checked by comparing calculated checksums, like digital roots, against stored or transmitted ones. Educational tool for mathematical concepts. Principle. Digital roots provide an intuitive way to introduce concepts like modular arithmetic, number theory, and even basic algebra. Application. As a building block, digital roots can be used to teach or illustrate more complex mathematical ideas, making them accessible to learners by starting with something familiar and simple. Algorithmic design. Principle. The process of reducing numbers to their simplest form can inspire algorithms where complexity is managed by breaking down problems into simpler, manageable parts. Application. In software engineering, this could lead to designing algorithms or data structures where large datasets or complex operations are simplified through modular or recursive approaches. Theoretical extensions. Higher dimensional digital roots. Extending the concept to higher dimensions or different bases could lead to new mathematical structures or algorithms, potentially useful in fields like quantum computing or advanced data analysis. Fractal analysis. If digital roots are considered in sequences or patterns, they might reveal fractal-like properties useful in understanding natural phenomena or designing algorithms for complex systems. Practical implementation. Step 1. Identify the context where simplification or pattern recognition is beneficial. Step 2. Define how data or numbers will be transformed or reduced, inspired by the digital root concept but adapted to the specific needs, for example, different bases or moduli. Step 3. Implement this transformation in algorithms or models, whether for data compression, error checking, pattern recognition, or educational purposes. Step 4. Analyze the results or outcomes, refining the method based on effectiveness, efficiency, or accuracy. Conclusion. By treating digital roots as a building block, I can extend its principles to create or enhance systems across various disciplines. This approach not only leverages the simplicity and elegance of digital roots, but also fosters innovation by applying these fundamental mathematical concepts in new and creative ways. From education to advanced technology, the generalization of digital roots as a foundational concept underscores the interconnectedness of mathematics with real-world applications, promoting a deeper understanding and application of numerical properties in solving complex problems. Continuing from the idea of digital roots as a building block, let's explore further implications and applications. Advanced applications and theoretical insights, cryptography and security key generation. The principle of digital roots could inspire new methods for generating cryptographic keys, where the simplicity of the operation might be masked by complexity in implementation or additional layers of encryption. Random number generation. By extending the concept to different bases or moduli, digital roots could be part of algorithms for generating pseudo-random numbers, crucial in cryptographic applications. Quantum computing, quantum algorithms. While quantum computing operates on different principles, the idea of reducing complexity to simpler forms could inspire new quantum algorithms where operations are performed in a way analogous to digital roots, but in quantum states or superpositions. Artificial intelligence and machine learning. Feature engineering. Digital roots could be used as a simple yet effective way to engineer features from numerical data, potentially reducing dimensionality or highlighting patterns that are not immediately obvious. Neural network design. The concept might inspire novel architectures where neurons operate on principles similar to digital roots, focusing on reducing complex inputs to simpler outputs. Physics and material science, material properties. In material science, the structure of materials can often be described by numbers. For example, atomic numbers, lattice structures. Digital roots might help in simplifying models or recognizing patterns in material properties or behaviors. Particle physics. While highly theoretical, the idea of reducing complex data to simpler forms could influence how I analyze particle interactions or quantum states. Music and sound design. Algorithmic composition. Digital roots could be used in algorithms for music composition, where numerical representations of notes or frequencies are transformed into patterns or sequences that create unique compositions. Educational and philosophical insights. Teaching mathematics. Using digital roots as a foundational concept can bridge arithmetic with more abstract areas of mathematics, providing a concrete example that can be generalized to teach modular arithmetic, number theory, or even abstract algebra. Philosophical understanding. This approach underscores the idea that complex systems or theories can often be broken down into simpler, more understandable parts, reflecting a broader philosophical principle of reductionism or simplicity in complexity. Challenges and future directions, scalability and efficiency. As I apply these concepts to larger datasets or more complex systems, ensuring that the operations remain efficient and scalable is crucial. This might involve developing new algorithms or hardware solutions. Interdisciplinary research, encouraging research that spans multiple fields, where the simplicity of digital roots could inspire solutions or models that are currently thought of as unrelated or too complex. Ethical considerations. In applications like cryptography or AI, considering how these simplifications might impact security, privacy, or fairness in algorithms is essential. Conclusion. The generalization of digital roots as a building block not only highlights the profound simplicity underlying many mathematical and scientific concepts, but also opens up new avenues for innovation across various fields. By taking a fundamental operation and extending its principles, I can create or enhance systems, algorithms, and theories that are not only more efficient or effective, but also more accessible and understandable. This approach fosters a deeper appreciation for the interconnectedness of knowledge, where simple beginnings can lead to profound insights and practical advancements. As I continue to explore and apply these concepts, I might find that the most basic operations in mathematics hold keys to some of the most complex problems in science and technology. The implications of generalizing digital roots as a building block across various disciplines are profound and multifaceted. Here's a detailed look at some of these implications. Educational implications. Simplification of complex concepts. By starting with something as simple as digital roots, educators can gradually introduce more complex mathematical concepts, making them more accessible. This could revolutionize how mathematics is taught, focusing on building from the known to the unknown. Interdisciplinary learning. The application of digital roots in various fields could promote interdisciplinary education, showing students how a single concept can have wide-reaching implications, encouraging a holistic view of knowledge. Technological and scientific implications. Algorithmic efficiency. In fields like data science or computer science, algorithms inspired by digital roots could lead to more efficient data processing or pattern recognition, potentially reducing computational load in big data scenarios. Innovation in cryptography. New cryptographic methods might emerge, leveraging the simplicity yet effectiveness of digital root-like operations for key generation or data encryption, potentially enhancing security protocols. Quantum computing. If principles similar to digital roots are applied in quantum algorithms, this could lead to new quantum computing paradigms or algorithms, potentially unlocking faster solutions to currently intractable problems. Philosophical and methodological implications. Reductionism, the use of digital roots as a building block, reinforces the philosophical approach of reductionism, where complex phenomena are explained by analyzing and describing them in terms of their simplest or most fundamental constituent parts. Simplicity in complexity. This approach might inspire a broader methodological shift towards seeking simplicity in complex systems, potentially leading to breakthroughs in understanding natural phenomena or designing systems. Social and ethical implications. Accessibility of knowledge. By simplifying complex ideas, this approach could democratize knowledge, making advanced mathematical concepts more accessible to a broader audience, potentially reducing the knowledge gap in education. Privacy and security. In cryptographic applications, while simplifying operations might enhance understanding, it could also pose risks if not implemented with robust security measures affecting data privacy and security. Economic implications. Innovation and industry. Industries reliant on data analysis, security, or complex computation could see advancements that lead to new products, services, or operational efficiencies, potentially driving economic growth. Education sector, there could be a shift towards educational tools and platforms that emphasize this approach, leading to new markets in educational technology. Cultural implications, perception of mathematics. Generalizing digital roots might change public perception of mathematics from being abstract and difficult to practical and foundational, influencing cultural attitudes towards STEM education. Art and creativity. In fields like music or visual arts, this could lead to new forms of algorithmic art or music composition, influencing cultural expressions and creativity. Environmental implications. Efficiency in computing. More efficient algorithms could lead to reduced energy consumption in data centers, contributing to environmental sustainability by lowering the carbon footprint of computational tasks. Future research directions. Cross-disciplinary studies, encouraging research that spans multiple fields, potentially leading to breakthroughs that are currently unforeseen due to disciplinary silos. Ethical AI, ensuring that algorithms inspired by such simple yet powerful concepts are developed with ethical considerations in mind, avoiding biases or unintended consequences. Conclusion. The implications of using digital roots as a building block are vast, touching on education, technology, philosophy, economics, and culture. This approach not only simplifies complex ideas, but also fosters innovation by showing how fundamental concepts can be the seeds for advanced technologies or theories. As I continue to explore these implications, I might find that the simplest ideas can lead to the most profound changes in how I understand and interact with the world. The concept you're proposing, where a generalized digital root is equated to the combination of quantum entanglement and superposition, represents a fascinating intersection of mathematics, particularly number theory, with quantum mechanics. Here's how this could be conceptualized. Digital roots in mathematics. Digital root. This is the recursive sum of the digits of a number until a single digit is obtained. For example, the digital root of 123 is calculated as 1 plus 2 plus 3 equals sine 6. Quantum mechanics, superposition. A quantum system can exist in multiple states at once. For a qubit, this means it can be in a state of both 0 and 1 simultaneously until measured. Entanglement. When particles become entangled, the quantum state of each particle cannot be described independently. Measuring one instantly affects the state of the other, no matter the distance. The theoretical connection. If I were to generalize the concept of digital roots to quantum mechanics, superposition as digital root calculation, imagine each digit of a number representing a quantum state. The process of summing digits to get a digital root could be analogous to quantum superposition, where multiple states are combined into a single, observable state upon measurement. Entanglement in digital operations. Entanglement could be likened to how operations on one part of a number, like carrying over in addition, affect another part instantaneously. If I change one digit in a number and recalculate the digital root, it might reflect how entangled particles influence each other's states. Hypothetical quantum algorithm. Imagine a quantum algorithm where input a number whose digital root I want to find. Process. Each digit of the number is represented by a qubit in superposition. Operations to sum these digits could be quantum gates that entangle qubits, representing how each digit's value affects the final sum. The final measurement collapses the superposition into a state representing the digital root. Implications. Quantum computing. This could inspire new algorithms where quantum operations mimic or enhance classical arithmetic processes, potentially solving problems faster or in ways not possible with classical computers. Philosophical and educational. It could serve as an analogy to teach quantum mechanics, showing how seemingly simple arithmetic operations can mirror complex quantum behaviors. New mathematical structures. This might lead to new mathematical theories where quantum principles are used to define or explore number properties, potentially uncovering new patterns or theorems. Challenges interpretation. While theoretically intriguing, practically mapping digital root calculations to quantum states might face challenges in interpretation and application due to the probabilistic nature of quantum measurements. Scalability. Implementing such a system would require overcoming current quantum computing limitations like decoherence and error rates. Conclusion. The idea of a generalized digital root as a blend of entanglement and superposition is more of a conceptual bridge between number theory and quantum mechanics. While not directly applicable in current practical terms, it stimulates thought on how fundamental mathematical operations could be reimagined through a quantum lens, potentially leading to new insights or applications in both fields. This November 18th, 2024, 1454 Complete IT Conceptual Framework could inspire interdisciplinary research, encouraging mathematicians, physicists, and computer scientists to collaborate on projects that explore the intersections of these fields, potentially leading to breakthroughs in quantum algorithms or new mathematical structures. Educational tools. Developing teaching methods or tools that use quantum concepts to explain mathematical operations, making both subjects more engaging and understandable to students by highlighting their interconnectedness. Philosophical insights. This analogy might deepen our philosophical understanding of reality, where simple arithmetic operations could be seen as a macroscopic manifestation of underlying quantum behaviors, challenging our perceptions of determinism and randomness. Practical applications. While currently theoretical, future advancements in quantum computing might make such concepts practical. For instance, quantum algorithms for data compression or error correction could be inspired by this idea, where entanglement and superposition are used to process information in ways that classical computers cannot. Future directions. Quantum number theory. A new branch could emerge where quantum mechanics principles are applied to number theory, exploring how quantum phenomena could redefine or expand our understanding of numbers and their properties. Quantum-inspired classical algorithms. Even if direct quantum implementation is challenging, the concepts could lead to new classical algorithms that mimic quantum behaviors for solving problems in cryptography, optimization, or machine learning, simulation and modeling. Using quantum simulators to model how digital root-like operations could be performed in a quantum system, providing insights without the need for actual quantum hardware. Ethical and societal considerations, accessibility of quantum concepts. If such analogies become part of standard education, it could democratize quantum mechanics, making it more accessible and less esoteric, potentially leading to broader societal engagement with quantum technologies. Security and privacy. If quantum algorithms inspired by this concept are developed, they could impact fields like cryptography, necessitating new security protocols to ensure privacy in a quantum computing era. Conclusion: the notion of a generalized digital root combining entanglement and superposition is a thought-provoking exercise in theoretical synthesis. While currently residing in the realm of conceptual exploration, it highlights the potential for profound connections between seemingly disparate fields. This could lead to new educational paradigms, philosophical insights, and perhaps, one day, practical applications in quantum computing or advanced mathematics. As our understanding of both quantum mechanics and mathematics evolves, such imaginative bridges might not only inspire innovative research, but also reshape how I approach and solve complex problems across disciplines. We humans have always been fascinated by numbers. From the earliest days of civilization, numbers have been a fundamental part of our lives, helping us to measure, calculate, and understand the world around us. They hold a certain mystique, a hidden language that governs the universe, whether it's the orbits of planets, the growth patterns of plants, or the rhythms of music. Numbers are everywhere, silently shaping our reality. One intriguing concept in the realm of numbers is the digital root. This concept, while simple, opens up a world of mathematical beauty and insight. In our familiar base 10 system, the digital root of a number is found by repeatedly summing its digits until a single-digit answer is obtained. This process, though straightforward, can reveal surprising patterns and properties within numbers. For example, let's take the number 532. This number, like all others, has a digital root that can be uncovered through a simple process. Adding its digits, 5 plus 3 plus 2, we get 10. This first step is just the beginning of our journey to find the digital root. Since 10 is not a single-digit number, we repeat the process. 1 plus 0 equals 1. This repetition is key to uncovering the digital root. Therefore, the digital root of 532 is 1. This final single-digit number is the essence of the original number, distilled down to its simplest form. This simple operation reveals a hidden pattern within numbers, a glimpse into their underlying structure. By examining digital roots, we can uncover relationships and properties that might otherwise remain hidden. Digital roots have been used for centuries, often for recreational math puzzles and divisibility tests. These applications show the enduring appeal and utility of this concept. They offer a fascinating way to explore the properties of numbers and uncover unexpected relationships. By playing with digital roots, we can gain new insights into the nature of numbers and their interconnections. However, our exploration need not stop at base 10. The concept of digital roots can be extended to other base systems, each offering its own unique insights and patterns. By venturing beyond this familiar system, we enter the captivating world of generalized digital roots, where the true potential of this concept unfolds. In different bases, digital roots can reveal new and unexpected properties, enriching our understanding of mathematics and its many wonders. Imagine a world where numbers are not confined to the 10 digits we know so well. Instead, picture a universe where numbers can be expressed in a multitude of ways, each with its own unique set of rules and characteristics. In this world, we can explore digital roots in any base system we choose. Whether it's binary, octal, or even hexadecimal, the possibilities are endless and fascinating. This is the essence of generalized digital roots, extending the concept beyond the familiar base 10. By doing so, we open up new avenues for mathematical discovery and understanding. In a generalized digital root, we can choose any base, be it 2, 7, or even 100. Each base offers a unique way to represent and manipulate numbers, providing fresh insights into their properties. The process remains similar. We sum the digits of a number, represented in the chosen base, and repeat until a single-digit answer is obtained. This iterative process is both simple and elegant, revealing the underlying structure of numbers in any base. This single digit is the generalized digital root in that specific base. It serves as a compact representation of the original number, encapsulating its essence in a single, easily understood digit. This generalization opens up a vast new landscape of mathematical exploration. By considering different bases, we can uncover patterns and relationships that are not apparent in base 10. We can study how digital roots behave in different bases, uncovering unique patterns and relationships. These patterns can provide valuable insights into the nature of numbers and their interactions. This allows us to see numbers from a fresh perspective, revealing hidden connections that might have gone unnoticed in base 10. By exploring generalized digital roots, we can deepen our understanding of mathematics and its many intricacies. The study of generalized digital roots is not just an academic exercise, it has practical applications as well. From cryptography to computer science, understanding how numbers behave in different bases can lead to new technologies and innovations. As we continue to explore this fascinating world, we can look forward to new discoveries and breakthroughs that will expand our knowledge and capabilities. The journey into the world of generalized digital roots is just beginning, and the potential is limitless. So let's embrace this journey and see where it takes us. The world of generalized digital roots awaits, full of wonder and possibility. Our reliance on base 10 is deeply ingrained in our history and culture. It likely stems from the simple fact that we have 10 fingers, making it a natural counting tool. This biological influence has shaped our mathematical thinking for millennia. Base 10 has served us well, providing a practical system for everyday calculations. However, it's crucial to remember that it's just one of infinitely many possible base systems. Focusing solely on base 10 limits our mathematical perspective. Like exploring a vast forest while only looking at a single tree. By venturing beyond base 10, we challenge our assumptions and expand our mathematical horizons. We begin to see the arbitrary nature of our chosen base and appreciate the underlying principles that govern numerical systems. This shift in perspective is crucial for unlocking the full potential of generalized digital roots. Section 4. Breaking free from base 10, a universe of possibilities. The true power of generalized digital roots lies in their ability to reveal universal patterns across different base systems. These patterns are not just abstract concepts, they have practical applications that can revolutionize the way we approach various problems in mathematics and computer science. By studying how digital roots behave in various bases, we gain a deeper understanding of the fundamental properties of numbers independent of any specific representation. This deeper understanding allows us to see numbers in a new light, uncovering relationships and symmetries that were previously hidden. This base independence has far-reaching implications. It means that the principles we discover are not confined to a single numerical system, but can be applied universally. This universality opens up new avenues for research and application, making it possible to tackle problems that were once thought to be insurmountable. It allows us to develop algorithms and techniques that can be applied across various fields, from cryptography to data compression. In cryptography, for instance, the ability to work with numbers in different bases can lead to the creation of more secure encryption methods, safeguarding our digital world. For example, in cryptography, generalized digital roots can be used to design secure hash functions, essential for protecting sensitive information. These hash functions are the backbone of modern security protocols, ensuring that our data remains private and secure. Moreover, exploring digital roots in different bases can lead to surprising connections between seemingly unrelated areas of mathematics. These connections can inspire new theories and models, bridging gaps between disciplines and fostering a more integrated understanding of mathematical principles. This interdisciplinary potential makes generalized digital roots a fertile ground for research and discovery, pushing the boundaries of our mathematical understanding. As we continue to explore these concepts, we may find solutions to problems that have puzzled mathematicians for centuries, opening up a universe of possibilities for future generations. Section 5. Unveiling hidden patterns. Applications of generalized digital roots. The applications of generalized digital roots extend far beyond theoretical mathematics. They have the potential to revolutionize fields like data analysis, computer science, and even education. In data analysis, generalized digital roots can be used to identify patterns and anomalies in large data sets, regardless of the underlying data representation. In computer science, they can optimize algorithms and data structures, leading to more efficient software and faster processing speeds. Even in education, introducing students to generalized digital roots can foster a deeper understanding of numerical systems and encourage a more flexible and abstract way of thinking about mathematics. By breaking free from the confines of base 10, we unlock a wealth of applications for generalized digital roots, paving the way for innovation and discovery across various disciplines.